We should be live.
One sec. Verify. It might take a few seconds. I feel like we might already be live, but I'm not seeing us live at the moment. Just give me one sec. I've noticed this pattern where it takes a while for me to see that we're live. Okay, yeah, we're live now. Let's
Okay.
do it.
All right. Hello, everyone. Welcome to today's brand new episode of Courtcast. I am your host, Tim.
And I'm Sahil. Welcome, everybody, to a brand new exciting episode of Courtcast. Before we get started, a few logistical things. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to it. So without further ado, let's get to it. So Tim, we've been talking a lot about quantum mechanics and diving into various facets of it, and then also discussing it in a cosmological type perspective. And I think our motivation for doing this episode was to kind of tie up this discussion of quantum mechanics in a nice bow tie, with probably a very well-known formulation, which we'll get into. So I guess just to kind of set the groundwork, we've been talking about quantum mechanics in terms of this object called a wave function, which we'll cover in a little bit. And then we also discussed something called the amplitude as well, which is very interesting. And so wanted to get your thoughts on like, why are we introducing this new concept? And, as we stated in the title of the episode, Feynman, formulated this and thought of quantum mechanics in this way. So kind of let's give the audience some motivation. Like why is this significant? Like why do we need a new way of thinking about this?
Yeah, and this ties back kind of to the origin of quantum physics. When quantum physics was just invented, it was almost like a complete overhaul of physics. In physics, back in the day, we talk about particles moving around. Like you have a table, you put some forces on it, then the position of the table will change and the velocity might change. Quantum physics, the way it's formulated, kind of throws a complete wrench in that story. And initially, instead of talking about these concrete things like positions and how fast something is moving, the math immediately jumps to something very abstract. We talk about states, we talk about mathematical objects like Hilbert spaces, and it just makes it very confusing for a lot of people, and probably a lot of our audience who don't have formal training, let's say in theoretical physics, will find that kind of mysterious in some sense. But and that's why for a long time physicists try to kind of get around that in some ways, to kind of make quantum physics a little more intuitive, a little more understandable. And indeed, physics has moved on, and we're going to talk about in this episode. And modern physics, for a large part, actually uses a kind of like or tends to use an alternative formalism called a path integral formalism. In such a way, we don't really talk about wave functions or states or all that much. But however, in the public point of view, we're kind of stuck in this wave function land, and then all these very complicated lingo about quantum physics remained, and that's why there's like a cloud of mystery around quantum physics. So hopefully, by going over some of these more modern concepts, we can dispel some of that.
Yeah, no, it's a great point. I mean, definitely when I was first learning quantum mechanics, it's very confusing to hear about like wave function collapse and other things that you mentioned, and it's definitely a departure from like sort of classical notions of position momentum that I have. So yeah, so why don't we start by laying the groundwork? So you mentioned several terms. I think it'll be helpful to define them. So first is, what is a wave function? We also talked about amplitude, and amplitude will be, from my understanding, like we can describe briefly and how it's related, and then of course the main enchilada. What is the path integral formulation? Like, what is that? So start with wave function first. What is a wave function?
Yeah, so this is kind of like quantum physics 101. The way quantum physics is different from normal physics is that quantum physics gives you one level of abstraction, and this abstraction traditionally taught comes in the form of a wave function. And this is synonym to like a state. You can think of it as a state of the world, or like imagine you're in a computer game, like, where all the players are, where how much health you have, how much magic you have, or how many coins you have in your character in an online game, kind of. That's kind of the state of the system, and we kind of abstractly think of the state of the universe, and this is something that the mathematics of quantum physics operates on. So, so at the most basic level, a state is just kind of where the system is at, basically.
Yeah. So then I guess, okay, so you described the state. Obviously the state transitions, like we're not in the same state. So what is that thing called, or what do you call that?
Yeah. So obviously physics is about change. If we're all in the same state all the time, that's not interesting. So it's the state change. The way the state change is categorized by, is captured by this concept called the amplitude, and we talked about previously. So a state and the amplitude is kind of inextricably linked. In order for you to get to a state, you have to transition. So in a certain lens, you can kind of think of a state as a subset of an amplitude. Because like, let's say I'm here. There was some history for me to let me to be here. So you can kind of think of a state as kind of a subset of that.
Mm-hmm. Can you, I guess, give it in terms of this video game analogy that you were making? Let's say the state is described by like the state of the world. All the players have like a certain amount of health, coins, magic, whatever, whatever certain properties. So can you describe like what would be the analog of the amplitude in this case?
Yeah, I would say the amplitude is kind of the history of what all the players have done up until this point, and of course including this point, and get to where they are. So I guess the amplitude is kind of more comprehensive. It's like the history of the entire server. Like imagine I don't know, the server crashed, your state is gone. You can recover that if you just have the amplitude. You can kind of like get it back, right? So in some sense, the amplitude contains information about the state. It's a more comprehensive object. It captures what happens in the past as well as the current, and possibly you can extrapolate that into the future, and possibly infinite future. So everything that has happened, everything that's happening now, and also everything that will or might happen is captured in sort of this amplitude. So it's a very general object,
Mm-hmm. So I know we'll talk about this a little bit later, but just to kind of give a little bit more concreteness to it, could you say it's like, this is really loose because I know these aren't the same things, but like, could you say very, very loosely that like it's related to something that is related to the probability of going from one state to another state? Like say the probability of like you say starting out the game, you have a certain amount of health and stuff like that, and you make it all the way to the final boss and you beat the final boss. Could you say the amplitude is something that's related to like the chances of you doing that?
Yeah, I would say it's not a bad way to talk about it, but I kind of intentionally want to avoid using the phrase probability because I think it confuses a lot of people. We have to remember that probability is kind of taught to, like, we learn about probability in high school and in college. It's very ingrained in us, but actually, like we discussed many episodes back, probability actually doesn't make sense very much in physics. So I kind of want to avoid talking about that concept. So yes, encapsulated in this amplitude, you can derive probability, right? But really, amplitude, and indeed, you're right that you can think of it as probability, but it's more than that. It's much more than that. It captures all the ways change can happen. I think that's the best way to put it. And I would say a lot of confusion of quantum physics comes to be when we insist on thinking of the world in a probabilistic way, when probability actually is not fundamental to physics, as far as I think we would believe.
Yeah, no, that's fair. I wanted to be very careful about giving that analogy because I know in the past we've talked about that there is a difference between classical probability and these like amplitudes or quantum mechanical analog of probabilities. So I'm just trying to give the audience a sense of like what is one useful thing that you can get from this amplitude?
Yeah.
So,
Yeah.
Okay, so we've described. Yeah, I'll go ahead. Sorry.
Yeah, I actually want to bring up a very, very good analogy. The analogy is you can think of it as a rope. Okay? Imagine you have a rope. The rope has a beginning and the end, right? The beginning, you have a state. That's what a wave function or a state would be. And the end, there's also a state. So the beginning and the end of the rope, you can think of that as the state or the wave function, whatever you call it. But if you think about the whole rope that links the beginning and the end, and it also contains the beginning and the end, that's kind of the amplitude. Yeah. So that's a very good analogy, and I think we'll come back to that.
Yeah. I think that'll be very fitting for our discussion. Okay, so we've described the wave function, which is a state, and then amplitude is kind of describes like encapsulates all the different ways in which you can like the histories in which you can get from one state to another state. Now, where does path integral formulation come in? Like, I mean, I know it's a large thing. Let's try to like, yeah, where do you want to start with this?
Yeah, I would say a path integral is a realization that you can actually compute. It's a method for us to compute the amplitude. And it's not obvious that it could be done that way, but it turns out that it could. And the way it's structured is it gives us a very, very visual way to think about quantum physics. And that's why it's so powerful. And that's why it's pretty much used throughout modern physics these days.
I see. So, okay. So what advantages does path integral formulation actually give you? Like, actually before that, let's describe like, how do I think about, so, okay, originally I have a wave function, which is state that somehow transitions through time and then ends up being another state, that we observe, or maybe not so much observe, but how do I think of path integral formulation? How do I relate one to the other? So yeah, in terms of this wave function amplitude that we described, how does that relate to the path integral formulation?
Yeah, and I think it's helpful to think more in terms of real world. I know we've been talking in abstraction, and that's actually not that helpful in physics, right?
Okay.
So in ordinary quantum physics, let's say I'm sitting here talking to you all, right? And in quantum physics, I'll be in a state. I'll be in a state of giving this podcast. And then you can have, if Schrodinger comes in, physicists come in, they'll say, hey, here's an equation, Schrodinger equation. You can solve it and you'll find out what I'm going to say next, right? That's how physics works. Let's say you solve it and you find out what this podcast is about. So that's very non-transparent. It's just some magic math that gets you from point A to point B, right? Okay. Now, the idea of path integral is to realize that, hey, look, when you do this process, you can actually do it incrementally. So what do I mean by this? This is kind of Feynman's genius when he realized this, right? He realizes that, look, I guess they actually didn't originate from Feynman. I don't want to give him all the credit. He popularizes the path integral, but the concept of path integral, I think, originated from Wiener. I think I forgot his first name, and then I think Dirac did some work in it, but then Feynman really took it and run with it, and he showed that it's the same if we produce Schrodinger's equation. But anyway, history aside, I want to give proper credit. But one of Feynman's genius, and I think that's part of in his lectures and in his path integral books, is to kind of do this visual exercise, right? Like, imagine I am going from, like, let's say I say one sentence after the next. He realizes that everything, and this is kind of an analogy on everything that happens, right? Like a particle go from here to fly from here to China, from US to China, right? Everything has a path, has a trajectory. When I'm trying to say something, there's a trajectory of words I'm going to say. He says that he kind of imagines, what if you chop that up, right? Like, imagine I say one character, one word, one sentence, right? The progression from 1 to 3, in the middle, somewhere in the middle, you have to go through 2, He realized that in quantum physics, the math just kind of works out that every progression, you can chop it up by smaller and smaller pieces. But you can't just chop it up, right? Something's got to give, right? The compromise is that if you chop it up, you have to consider all the possibilities. right? That's what he realized. And then he realized that, hey, look, if you follow every single possible outcome, every single possible trajectory, and you chop them up to all these individual possibilities, and you sum them up in some particular way, it turns out that you can calculate this transition, right? So basically, like, imagine I'm going to give this podcast. Maybe in Feynman's calculation, he'll go through like, hey, look, what are all the possible words Tim can say, to make sense with the podcast? Just kind of add it up with some weight, some factor, sum it up. Then eventually he'll get the whole amplitude of this podcast, right? And that's kind of the genius realization that you can do it this way. And why is that helpful? Is because, instead of just, hey, there's some magical math that gives you from A to B, here's kind of like a visual way to think about how to get from A to B. And of course, there's also math behind it.
Mm-hmm. I see. So, okay, so let me try to see if I can like summarize what you just said. So essentially, if you look at the way, initially people are taught quantum mechanics, they're like, oh, here's this Schrodinger's equation, which tells you how the wave function evolves with space and time. You solve it numerically or analytically, and then you get something, and how it's going to evolve in space and time, but it's a little bit confusing, like what this actually is. Instead, what I could think of is like, I start off from some state, and I want to say like, okay, what is the, me ending up in another state, and I look at all the possible paths from like point A to point B, and essentially each path has a certain weight to it, because we know the endpoints of the path. Of course, is an abstract space because you're saying states itself, but for conceptualization, we can go with points. So you start off from point A to point B, draw many different paths, and then each path itself will have a certain weight of, not to say how likely it is to happen, but how much it contributes to what you're trying to compute, which is the amplitude. And then you sum all those together and you end up getting your amplitude. Is that a fair way of stating this?
Yeah. And basically, so and in some sense, you can argue that Feynman didn't do anything new because the math is exactly the same. He just conceived of a different way of thinking about the calculation. So on the one hand, you have something that satisfies the Schrodinger equation. This is very complicated mathematics, differential equations and whatnot. And he said that, hey, look, if you think of this object as a path integral, it's just summation of all possibilities weighted in some ways. Hey, it happens to satisfy your math, right? So they're equivalent. The two objects, the wave function or the amplitude, satisfy both the same equation. So there's the same object. But then the leap of faith is kind of that, let's just forget about the equations now. Let's just think of our objects,
Okay. And then last question I have about this is like, okay, so, Schrodinger's equation gives you the dynamics of the system, much like in classical mechanics, Newton's laws give you the dynamics of the system, of how it'll behave as you progress through time. Where does this like dynamics of the system come into the path integral formulation? Like, how do I think about that?
Yeah, I think the physics of it comes down to how much you will weight certain path, right?
Okay.
Yeah, but I think the first order of business is that it makes a philosophical difference, Like imagine I'm trying to calculate something. Let's say I have an electron on my hand. I want to say, well, how is this electron going to go? Is it going to go up, down, left, and right? How is it going to move, right?
Yep.
On the one hand, I can just be a calculator, just solve an equation. I get the answer, I get a answer, I can, if it's a homework problem, I submit it to the professor, sure, you get an A, great. But like, it's empty, you know what I mean? Like, I just did a calculation. That's not interesting, right? But if you use Feynman's perspective, you can say, well, imagine if the particle is conscious. I don't like to think of it this way. There's nothing supernatural about it. But like, imagine the particle is thinking. What is it really thinking? What is the particle calculating in order to know what to do? If you take the path integral formulation, which is mathematically equivalent, you can say, well, hey, look, the particle is really considering all the possible path, and maybe let's say the answer is going straight, on average at least, because quantum physics has some randomness in it. Like why did the particle decide to go straight, given that it has all these possibilities in the path integral? It's summing all up.
Mhm.
There
Mhm.
must be, in this way, there must be some kind of cancellation. Maybe like the amplitude of going up, or in the calculation of the amplitude, going up and going down has an equal and opposite sign. It cancels out. So the only thing that didn't cancel out is going straight. And this is how you would
Mhm.
explain why a particle goes straight in this formalism, as opposed to solving an equation, you know?
Mhm. Can can you give this analogy in the context of, like, say you had two electrons? So if we're considering all possible paths, there exists a path with which two electrons can approach each other, but we know from like classical electrodynamics that two light charges repel each other. So how do you reconcile that? Like how can I think about that in terms of path integral formulation is more of what I'm trying to ask.
Yeah. So in ordinary physics, you would just say, oh, there's some equation you can solve. But in
Hmm.
ordinary physics, you also have certain principles, like electrons together, they might try to minimize energy. Although I'm using energy loosely, there's usually some other function you try to minimize. But let's say it's trying to minimize energy, right?
Yeah.
And that's how we explain certain things in physics, right? Like if you have two electrons of the same charge, when you push them really close together, there's a lot of energy because they repel each other. They don't like to do that,
Hmm.
so they'll move
Hmm.
away. And if you put
Hmm.
an electron and a proton together, the electron it's gonna want to circle around the proton to make an atom, the hydrogen atom, right?
Hmm.
It's because
Hmm.
the attractive, you minimize the energy when they come close.
Hmm.
If you jump to quantum physics, it's very hard to get the same concept because like I have this wave function moving up and down. Like how do I get the same intuition? But path
Hmm.
integral comes to the rescue, because remember, path integral has this weight. You can say that, and if this weight is linked to the energy, it might accentuate the possibility where the energy is minimized. They will have less cancellation.
Hmm.
And if you have energy that are much higher, going up and down might cancel violently with one another. And that's why at the end of the day, once you sum up all these possibilities, a lot of them cancel, and you end up seeing the parts that are consistent with minimizing the energy, and that's how reality emerges in this path integral picture.
I see. I see. Okay. Um, so I guess like one thing that's very curious. I mean, we described it through this example that like two like charges will repel each other. That's what I would consider like classical behavior. So based on classical mechanics. How does classical mechanics arise from the path integral formulation? Or rather, yeah.
Yeah, I would just say actually the path integral formulation is very natural because in normal
Mhm.
physics we think of objects as going through one path. The electrons will definitively go through one path. That's it. The
Mhm.
path integral formalism is just saying that, hey, look, let's consider all possible paths. In normal ordinary physics, you might just say that, well, let's say two electrons come together, they'll repel. That's just one possibility.
Mhm.
You just sum up one possibility, and everything else will be zero. This one possibility will have
Mhm.
infinite weight. That would be the path integral, right?
Mhm.
And then that'll be the classical picture, right? But if you have a path integral, it's a little more nuanced. It says that, hey, look, this ordinary path, maybe you still have a really high weight, but then if you slightly move away a little bit from that, it's not impossible, but there's still a little bit left. Maybe it's like 1,000 instead of 10,000. Well, but more than that, it actually can have complex number as well. But I don't want to get into the complexity of that. Pun may be intended, but uh, but because you remember in quantum physics, things can be in superposition of one another. They can be all mixed up. So it makes sense that the possibilities should be able to get mixed up, and path integral kind of takes care of that naturally. But it's just you consider all the possibilities.
Yeah. Okay, so what you're saying is that like it can happen, but there would be, I guess, a lower weight, some weightage scheme associated with that. And then if I guess if it deviates too much away, it's unlikely to happen. And then also like different paths cancel each other out. So what you get left with most likely to happen is the what I call the classical path, like a thing moving in a straight line if there are no forces or it's empty, purely empty space. Is that a fair analogy?
Yeah, that's kind of a fair analogy. Although again, I would like to caution that whether something is likely to happen or not, the likelihood of something happening, it's a very classical intuition. I mean, it's been drilled into our heads that whether maybe it's going to rain tomorrow. That's just our way of viewing the world. Like fundamental physics doesn't really give a likelihood, but it does give an abstract way of adding on and subtracting these possibilities, these paths, basically. So.
Yeah. Okay. So essentially the classical mechanics arises because all the other paths, I don't want to say are less likely, but have a certain weighting scheme such that their contributions either cancel each other out or are negligible. Is that okay? Is that a better way of saying it?
Yeah, you can think of it this way, but I actually like another viewpoint, right? It's because
Okay.
the other paths, the other possibility, let's say the electron fly to Andromeda and come back, or like
Hmm.
left to the end of the universe and came back. Those are really
Okay.
violent possibilities. And
Yeah.
those possibilities, because they're not consistent with some of the things that we're calculating, like like let's take the energy. The energy for that to happen has to go really high, really low, like going crazy, right? When you have a lot of fluctuation like this, when it's so inconsistent with kind of the math that you're putting in terms of energy, momentum, and different things, they tend to cancel out. They tend to look like noise, right? So this is kind of like and this picture also kind of gives you an idea of where does the noise of the universe comes in. I think these are the other possibility that doesn't really fit in. They kind of just add up, and because they're not coherent, they didn't fit into any of the the energy or whatever we were computing. They just kind of how do I put this? It's almost like you tune your radio, right? Like if you tune to the right frequency, you start hearing like, hey, look, the podcast is saying something interesting. And if you just go a little away from it, it's just noise. That's what it is. Like the path integral is kind of like a little radio knob. It's like, hey, look, if you tune to the right paths, kind of like a pattern emerges. And if you a little tune away from it, like even like imagine this. Even if the electron really is flying to Andromeda and back, we're not going to keep track of it. There's no way, right? We don't have the technology to keep track of it. It's still just going to look like noise, right? So that's kind of what's happening. I think like a radio is a kind of a pretty good analogy.
Yeah. Actually, that segues nicely into my next question is, how can we, I guess, interpret experiments from a path integral formulation? So, say I like, I'm measuring a certain property of a particle, spin, or maybe like if I take the double slit experiment and I look at which hole it went into, how would I think about that in terms of path integral formulation?
Yeah. So I just want to say one thing. I know some of our audience might have a little bit of training in maybe an introductory course in quantum physics or listen to podcasts or whatever. There's sometimes there's an explanation that's given like this. It says that, hey, if you look at a particle, its wave function collapses into where you're looking at it, and that's why you see pattern. When it's like you see a different pattern if you were looking at the particle versus you're not looking at the particle.
Can you briefly, very quickly describe what wave function collapse means for those who don't know? But yeah.
Yeah. Basically, it's this notion that like for example, if you have let's take an example. Let's say let's say my hand is in a quantum mechanical state. It's in a mixture of both left and right, because in quantum physics that could happen, right? And then my hand goes through some quantum mechanical thing, and then it might turn into something else. And then the idea of wave function collapse is if someone just look at my hand, They can only observe whether my hand is on the left or on the right, right? You can't see in between. And that act of seeing my hand collapses my hand into like finding a position to the left or to the right. That's how quantum physics is usually taught to people, right? And
I see. So like if you were, I mean, you've also described it in terms of the analogy of like a quantum coin, that if you flip it and it can be either in heads or tails, and it comes out to be heads, then definitively like the other state is irrelevant now. And now you know it's like in the state of heads.
Yeah,
or something like that.
Yeah. So it gives people this illusion that there's something magical about the mind or something. It's like, hey, look, like what if I see it but didn't think about it? Was my hand on the left side? Like it just makes it so confusing. So let me just say that, like that's an okay way to think about it, because Feynman once said, just shut up and calculate. It'll get you the right answer. But that's confusing as heck. So I would say it's wrong. Let's just say it's wrong. Like, don't think about quantum physics like that.
Okay.
Yeah. So I would say
Oh no, go ahead. Sorry.
I would say the path integral actually gives you another way to think about it that does not involve any crazy wave function collapse, any spooky mind quantum physics connection, nothing like that. It's just very natural.
Yeah. So I guess like and also I mean I think the wave function collapse refers to that, like, wave function you can think of as a wave, and if you collapse it, like collapses on like a single value or something like that, and all the other values no longer have like a 0% chance of being observed, or something along those lines. But yeah, I guess how does path integral formulation avoid wave function collapse?
Yeah, and I think the crux of this argument is to remember that we ourselves are quantum mechanical. Like even if you were running an experiment, maybe it doesn't look like it's quantum mechanical, but inherently, the entire world is quantum mechanical, right? Now, imagine this thing. I mean, this double slit experiment is basically saying that you send a particle through a double slit, which is two slit. And you ask the question, did it go through the left side or the right side? And if you try to look, you see definitively it goes to the left side or the right side. But if you didn't look, you see kind of like a really fantastical rainbow pattern, which is saying that it neither goes to the left or the right. It goes to both slit at the same time. So it's kind of like mind-boggling for some people, right? So how does the path integral kind of make that a little more intuitive? Well, we have to remember that it's not that it's not that the change in perspective is that it's not that the quantum system has changed. It's because we are focusing on different parts of the quantum system, right? What do I mean by that? Look at the paths. Look at all the possibility, right? The possibility is that, hey, the particle could go to the left. That's it. It could go to the right. That's a possibility. Or it can go to both at the same time and interfere, right? Let's say these are three possibilities. And in the path integral, they're all represented in the path integral, And if we as experimenter, we look, let's say we observe the particle going to the left, right? The path integral didn't change, but we happen to hop on around the paths that go to the left. It's we who are changing. Because we kind of just happen to choose to focus we happen to observe or focus our attention to the parts of the path integral that have the particles go to the left possibility and not the other ones. And that's why all the calculation afterward, we will have to take that into consideration, right? There could have been another Tim observing the other possibility, and the path integral will contain all of it, But our world has to choose one. We observe only one. So we chose one of the possibility, and we did that calculation, and just mathematically, the result that you get from doing that path integral calculation is exactly the same as if the wave function collapsed, right? So you can show that actually.
So I just want to understand this a bit more. So you're saying that like quantum mechanically, the system goes through all the different possibilities. They just don't. They're still there. It's just that. I mean, the mechanism of how we choose a path is also maybe maybe we can talk about that a bit later. But somehow some path is chosen, and we're on this path. And I'm just trying to understand because I guess like this it's very abstract. How do I think about like what path was chosen, or like in the case that it went through the left when observed, is it, yeah, because so far I mean, yeah, I just want to understand like yeah, how do I think about like the path of the
Mhm.
left being chosen given all the other stuff that is happening? Yeah, just can you explain that a little bit more?
Yeah, and this comes back to kind of the consistent, and what I'm describing is the consistent history interpretation, right? It's just saying that
Mhm.
look at all, you kind of have to go through a bird's eye view. Look at all the possibilities. And if you look at all the possibility, you also have to include the experimenter, right? Because
Mhm.
as an experimenter, I'm not isolated from the quantum mechanical system itself. I'm part of it,
Mhm.
right? So traditionally, you might think that, oh, the path integral only applies to the particle. Oh, the particle might go through one slit, two slit, both at the same time, whatever, right? But actually, no. The path integral contains particles go to the left, I observe it, and then go to the screen. Particle goes to the right, I observe it, go to the screen. Like, I'm part of the path integral. You know what? And when I say, when let's say I go to my lab, I observe particle on the left. You know, I mean, I don't, and if you buy this kind of multi-world consistent history viewpoint, maybe there's another Tim in like a multi-world experiment. They will observe a particle going to the right and measure the right. Right? You have to go through all these possibility, and you see that look, it's not that the particle kind of chose one. We are just like, it doesn't matter what we do, we are just one part of the path integral. Like because there's nothing you can do that will really grant you a bird's eye view. We only observe one trajectory of the universe, right?
Mhm.
So we have to limit ourselves to that possibility. And when you see that, you're like, hey, look, then there's no collapse, right? Because there's another Tim in the multiverse observing the other possibilities. You see what I mean?
Mhm.
Which didn't exist in the original viewpoint, in the original quantum physics. It's just like, hey, there's a one wave function. It's just changing, right?
Mhm. Okay, so one question regarding that is like, in this, so I guess I'm just thinking how to really describe this. So you said we're like on this one path that like, we can only really see one path that the universe goes, and by path I mean how the states of the universe, quantum mechanical state of the universe transitions. We
Mm-hmm.
can't really see the other paths. But then I mean, how do you even know to consider the other possibilities? Or like why does that work if we can only really go down one path in some sense? I mean, you won't be able to realize the other paths, or how do you, yeah, I guess, can you like deviate away from the path that you're going down? Or yeah, I just want to understand that. It seems like we talked about multiple paths, but we can only realize one path.
Yeah, I mean, I think that a little bit of that it's metaphysics, because like indeed we only have one
Mm.
universe and we can only observe
Mhm.
one thing. And in quantum physics,
Mhm.
we keep talking. There's also this no cloning, no deleting, there's no hiding. There's a lot of these theorems related to like, you just cannot reproduce a situation, and you can also
Mhm.
never erase a situation, right? So
Mhm.
those are statements about like the existence of all these possibilities, and also linked to the fact that we only see one. Like part of that is just an unfortunate part of science, right? Like I guess like indeed when we make an observation, we have to make a determination. Like for example, if you try to measure the position of a particle, you are
Mhm.
insisting on the particle having a position, and the system will try to give you
Mhm.
that because you designed your
Mhm.
instrument to do something and give you a reading.
Mhm.
It will give you
Mhm.
that, because you're trying to do it. And by doing that, you're kind of forcing yourself into a path, basically. Like, the universe kind of has no choice. It just has to give you something, right? But then quantum physics deals with all possibilities, but we only are seeing one.
So are you saying that, like, we see one path because the questions we ask of the universe are framed in a particular way, so you kind of go down that, or is it truly like one path? Or I just want to tie it back to your point that you're mentioning.
I think it's because we insist on having these like we're insisting on things having a particular answer, and like like, for example, if you try to, like, if you flip a coin, one way or another, you're either gonna get heads or tails. Like, you're gonna reject the notion that the coin is somewhere in between, because that's just not how coin flip works. And this is the same in a quantum coin flip, But of course, quantum physics deals with both heads and tails. But you only got one. But like, when you do that, abstractly you can think of it as a fork, but it's not really, like. Well, of course, it's never totally black and white, right? Like, your machine could, like, screw up and whatnot. But like, we try very hard to get a definitive answer, and there are a lot of interactions in the universe that kind of really need to choose a side. Quantum physics will tell you how all the possible sides will evolve, but it doesn't tell you which one is chosen. And I believe the best policy is to think that maybe all the possibilities were chosen. We just happen to be in one of them.
Yeah. So I also want to state for the audience that you mentioned the word like multi-world or something like that. I want to also make sure that we're not confusing with many worlds, which is a different interpretation of quantum mechanics that states when something happens, the universe branches, and there have been a lot of popular videos describing like Everett. I think the guy's name was Everett, who came up with this many worlds interpretation. And this is different in that sense, where based on what I'm saying from you, all the possibilities exist. We're just, in our limited scope of what we can observe and know, we're traveling through this one path in many possibilities, and all the other possibilities are essentially out of reach in some sense, or the one. Yeah, is that fair to say?
Yeah. It's true. Like this is, I mean, there is, like, this is technically closer to the consistent history interpretation, as opposed to what you mentioned, the multi-world interpretation. I mean, you can argue that this is a matter of philosophy. I mean, you can argue that the different possibility exists in different multi-worlds, but at the end, it's just a name. They are out of reach, because they exist in the different paths that is inaccessible to us. So.
Yeah. Actually, so this is actually a nice audience question that came in, that I think ties well to experiments. I'm going to paraphrase the question in a different way to tie it towards here, but essentially, like, how in the path integral formulation, how would you explain quantum entanglement, like the mechanism of it, how it arises, and whatnot?
Yeah, that's a great question. And and when you say entanglement, it means that things become highly correlated. And in this path integral, you can kind of abstractly think about the different paths particle takes, right? If one particle has nothing to do to another, in an abstract way, their paths don't cause a change to one another in this way. You can kind of think of them as, like, if you think like that rope analogy, like, there's not a lot of crisscross in the paths that they travel. Entanglement will arise when the path of one particle really influences the path of another particle. Is that their paths will have many different ways of crisscrossing back and forth, and this is how you can measure some of these entanglement. And I think they also let me think. Like I think this gets technical. Like, people use the path integral to calculate something called the entanglement entropy and it's related to this way of I guess I won't say too much further, but you can visualize entanglement as kind of like a linkage, or like there's that definitely a way to frame it in terms of this path, but I don't think I can come up with a good analogy right at this moment.
So okay, let me take a stab at an analogy based on what you've said before. So, I mean, you mentioned the rope analogy, like you have a rope at 2 points, and it's wiggling in some way. So if these things are correlated, let's say as I'm moving one rope up, it has like a peak, and like parallel to that, the other rope it would have a trough, and then vice versa as you go along the ropes, and so you would then say, oh, these ropes are like perfectly correlated or anti-correlated, but I'm just going to take the absolute value notion of this. So say that they're heavily correlated with each other or perfectly correlated with each other. And so that would describe, so if you could see that in terms of the path integral for two different particles of influencing each other, then would you say they're like maximally entangled with each other? Is that a fair analogy? Or
yeah, I would say so. Yeah, like certainly the paths, when you sum up the paths, it's got all the possibilities. But then yeah, if you see that the possibility that gets highlighted are the ones that they are influencing one another, then yeah, that would correspond to entanglement, probably.
Okay, so now this brings up another question, which is we describe path integral in terms of like you have some state, which is the state of the universe, and then you have a different state that it ends up at, and then you look at how it like transitions and look at all the different possibilities of going from one state to another state. But here we talked about two particles, and if these particles are part of the universe, like how do I think about that? Because originally I thought it was like one object moving from one state to another state, but here now we're talking about two particles, which seem like two, not just separate objects, but like separate but correlated objects, transitioning through time or whatever variable of interest. So my question for you is like, which one is it? Is it like a single path in this abstract space, or is it like many paths? And then how do you distinguish between different entities that are correlated, not correlated? Universe could be made up of patches of things that aren't necessarily correlated with each other. Possibly, I mean, this ties into like black hole physics and whatnot, but I don't want to go down that route for right now. But yeah, so how do I think about this?
Yeah, so like at the most simple version, and if you have kind of some toy model, you just have one particle in quantum physics, then yeah, the path integral will just be this one particle. But this is all theoretical, right? And in the lab, you can try to you can try to replicate that by trying really hard to isolate your particle, right? But of course we know that's not possible. So really, if you look at it cosmologically, there will only be one path integral, and that path integral will encapsulate every single entity in the universe. And you can ask, well, from what state to what state? You can perhaps go all the way from the beginning, and maybe the beginning it's not even anything anymore, when nothing existed, right? You can even trace it all the way back from when the universe was created, the state of creation of the universe, all the way to right now. Like this will be the ultimate path integral, And inside, and this path integral is a very complicated object. And also, by the way, the path integral is, let me just say, it's a technique of calculating something. And this object that is calculating is the amplitude, right? We're kind of using it interchangeably, but it's just, the path integral is just a viewpoint, how to view this amplitude, right? Okay. So within this path integral, there could be many different chunks that has nothing to do with one another, right? There could be like, I don't know, Andromeda might have to move, like how Andromeda moves has nothing to do with how our own Milky Way moves. Well, it has a little bit to do with it, but not too much. But then maybe like if you trace it back early enough in the universe, some of the paths of the particles that are related might crisscross, right? And if you go back all the way from the beginning, at some point maybe all the paths will intersect in some ways. So as an object, yeah, it's very grand. It has almost like an infinite amount of structure in it. Just chunks here and there, different correlation, entanglement, whatever you name it. But it's a, we can probably never compute it fully, but it's good to like think of this as a abstract object to understand how, to the best of our knowledge, this is how the world works.
Yeah, that's fair. So I want to ask this following question of how does classical probability arise from the the path integral formulation? Like, for instance, describe it to me in terms of like flipping an actual coin with like, it can be heads or tails. How do I relate that?
Yeah. Well, of course, flipping a coin is a little bit different because there are a lot of air molecules interacting with the coin, and there's a lot of chaotic dynamics. And you could argue that if you can really keep track of those air molecules, you can guess probably way better than average whether it has heads or tails, right? In terms of the path integral, doesn't exactly give you a probability, right? It gives you this abstract thing, and you might ask, well, it's how do you relate it to the real world, right? But now, but let's imagine this coin is quantum mechanical in some way, so that of course, it is ultimately quantum mechanical, but let's focus on the quantum mechanical aspect of it, right? So how this path integral gives you this illusion of like chance, right? And of course, quantum physics is random, but so if you look at, so what does it mean when I say I see the coin is heads? It means that for my future experiment, I have that knowledge, and I'm going to carry that forward. And in terms of path integral, it means that I'm focusing on the paths in the consistent history interpretation, like I'm on, if I want to calculate anything more in the future, I don't have to consider all the paths. I mean, you could, of course you could, but it's very hard, right? So I'm only going to focus on the paths where I see heads, right? And when you do that, if you focus on that portion, the rest of the path integral, you can simplify it by thinking of them as some kind of noise, basically, right? So basically, you're focusing on something that you're seeing, and ignoring the rest. But then you of course you can't totally ignore the rest. It's very complicated, the rest, but you can simplify it by thinking of them as effectively coming from the noise. Like one good analogy is like the digits of pi. It's like 3.14159 blah 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 whatever, right? I don't remember how many digits. Like, and if you don't know how many digits of pi if you don't know the exact digits of pi, but you might not know that, but you can still draw some conclusion of the digits of pi, right? If you look at 1 million digits of pi, roughly 1/10 of them will all be ones and zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, right?
Yeah.
And in that same vein, if we ignore different parts of the path integral, we can effectively approximate the rest of the stuff as if they were having random probability. And if you think of it in that way, then the reason why we observe like coin flips 50-50, part of that is because we have to choose a path to go down, but part of that is also because we're not able to take into account of everything, and so effectively we can simplify our math if we treat the thing as if they're probabilistic, and that's why everything seems like it's probabilistic.
Yeah, that makes sense to me. And then also, I mean, a number of our viewers on our Discord have talked about the notions of like free will and determinism. So wanted to see how the path integral formulation, if it can answer that, or how does it tie into that?
Yeah, and this is very interesting for me because I know like this is philosophy of physics. It's not exactly physics because like it doesn't affect observations, and then it's really like not exactly part of science. And in physics we don't really think of it very much because we're very focused on theory and experiment. But the path integral does kind of make a good point. It kind of completely throws some of those questions out of the window, basically. So first of all, let's talk about free will. What is this? And to me, free will is a very human concept. We like to think that we have agency. Like, hey, I don't know, like yesterday I decided to eat rice as opposed to noodles for dinner. I would like to think that I had a choice, right? I could have eaten rice or noodles, like no one's forcing me to do one thing or another, And in classical physics, there's a real conundrum. It's like, hey, what caused me to choose rice over choosing noodles? Was it ever possible? Could I have chose something else, right? But if you accept this path integral picture, like that's not even a question anymore, because maybe I ate both rice and noodles. But like in the path integral, I happen to eat rice, right? And maybe there's a Tim in the other part of the path integral eating noodles. So what is free will anymore? Was I free to choose? I don't know. Maybe I chose both, maybe, So it's kind of becomes a little bit mute. Yeah. And also the concept of determinism also becomes a little bit mute now. Like what do you mean by determinism? Because I know people like to think that quantum physics is non-deterministic. But is it though? If you think about the path integral, like all the histories are going together. All the histories are all summed up. It's just that we have to choose one. And we can't force ourselves to choose which one. It's just how the universe works. Maybe they're like 10 trillion universes happening at the same time. I mean, kind of an analogy. And we are only seeing this one. Does it mean that it's not deterministic? Like how does that work? Like it's deterministic if I don't like to use this word, but like if God existed, God will see all universes happening, we are one of them, we don't see the rest. Does it mean that we're not deterministic? It just kind of throws that question out of the window, I don't even know what determinism is anymore in this framework. So that just is interesting. I think like it completely like, in this framework, some of these questions just kind of like, I don't know. It's almost like you're asking the wrong question.
Yeah, no, it definitely interesting how it changes the framework of it. Um, my last question for you, last thing that we want to talk about is more speculative territory. Like, what would you say is beyond the path integral, and how does gravity factor into the path integral?
Yeah, I would say this is super interesting question because we know that, we know that our limit of science is probably limited, and from history, we have had theories that were proven wrong time and time again. And chances are quantum physics is probably not exactly right either. But I think we have to keep in mind that just because it's not right doesn't mean that it's completely wrong. So something like the path integral probably is right in some regime of validity. I mean, in many episodes back, we talk about regime of validity. So the path integral is definitely correct within some regime of validity. And it's quite plausible that quantum gravity will push it to its limits. Maybe there's string theory, and string theory also use the path integral, although much more complicated. But I would guess that, something like the path integral still would have to exist. But what it means to have different paths will probably change in some way. And we may be already seeing that in string theory, right? Like, the universe itself could have different shape, and those different shapes could have different paths. And maybe like our observable universe could be one path of the multiverse. And I don't exactly know how to think about that, but that's definitely interesting. I mean, this is like way beyond like what we can even observe. So it's hard to say, but probably there is something beyond.
Yeah, and you notice, I mean, when we were in discussion for this episode, you mentioned also like path integral involves like a starting and an end point, for lack of better words. But in gravity, is there really a start and end point, or does that even make any sense? Or
Yeah, I mean that's interesting because conventionally path integral has to do with space and time. You have a state at certain time transitioning to time one to time two. And of course there's relativity and path integral does accommodate that. But yeah, if you look at cosmologically, what happened to the path integral when time and space still does not yet exist? What is the path? Like, you know, I mean, in string theory, you can kind of define something more abstract, like there are paths of things in this more abstract space. I'm not sure. There could be a different space where space-time emerges, and these spaces could be more exotic. People have proposed something like that. But yeah, these are, yeah, I would say, well, let's just say that actually the path integral has never been defined mathematically consistently. So it has been defined good enough to physicist standards for us to do calculations. So even the mathematics of it's still a question. So it gives extremely good intuition, really good intuitions. But yeah, it's actually the logical consistency of it still escapes us, I think.
Mhm. Yeah, that's yeah, that is interesting limitations of it. I mean, but this is limitation with science even in general, not just pathological formulation.
Hmm.
So we're yeah, so we're almost at time. So I wanted to, our tradition of our end of our episodes to give the audience any words of wisdom that Feynman or the Path Integral have taught you.
Yeah, and I would say, I mean, there's a little bit of historical perspective. Like, I think when Feynman initially thought about the path integral, he really wanted to come up with an alternative to quantum physics, I think. And I think his genius was not appreciated by a lot of people because this is very complicated stuff, right? I mean, if he was able to totally have a new version of quantum physics, his achievement would probably, at least in the public's eye, might even surpass Einstein. But in my mind, he's one of the most brilliant physicists of all times. Absolutely. But I think he was disappointed that he realized that the path integral is equivalent to Schrodinger's equation. He was very disappointed. But now, of course, many years later, now I've learned it, and there's kind of like a level of poetic brilliance out of it. It's like you try so hard to get away from quantum physics just to rediscover it, but in this much more beautiful framework. And it kind of gives you this I would say almost like a religious experience. I mean, I don't like to talk about religion very much, but like, look, I mean, but you can't help but feel inspired, right? Like as a person, the only reason I'm here is because of the path integral that links everything back to the creation of the entire universe. I mean, are you kidding me? That's amazing, and that's just this path integral formalism. I mean, it kind of gives you a sense of the scale of the physics we're at. Like, even though I'm such a small creature in the universe, like I link to everything in the past, and I think that's inspiring.
Yeah, that's a wonderful way to sum it up. And so yeah, so on that note, I want to thank everybody for joining us. And we'll see you all next week.
Yeah, see you all next week. Bye bye.